Our lesson for today will be looking at Chemistry 1502. We are still busy with SN1 reaction. Lesson 102, let us start. Well, I did promise that we are going to look at the second example of SN1 mechanism. So we are going to start with the second example. Once we are done, we are going to look at other concepts which you need to understand under SN1 reaction. So let's say we have 1 iodo 1 methyl cyclohexane, let us not look at stereochemistry, just to explain this SN1 reaction. So we react this with methanol, which is the same nucleophile we had on the last example, CH3OH. So you can pause the video, try to work it out, and play the video to verify the answer. The first step that we need to represent under this mechanism is the formation of carbocation, which is the leaving group leaving our substrate. So this is the leaving group, actually leave the substrate. Then you set the forward reaction, normally it is less than the reverse reaction. And we have our carbocation here, plus our leaving group. Then step number 2, it is when the nucleophile will attack our carbocation. Forward is greater than the reverse, and then we are going to have this as our product, and then since we said if oxygen bonds 3 times, it's going to have a positive charge. Then remember that this is an alcohol. It will have to undergo deprotonation to form the product. So what happens is that we react the very same product with alcohol again. So what happens is that this hydrogen bonding electrons between oxygen and hydrogen will move to oxygen, and then we have pair of electron attacking this hydrogen. Then our final product, by the way, this is step number 3, deprotonation, and then we can go ahead and write our product. So our product, we are going to have plus hydrogen and oxygen with those lone pairs, and we have hydrogen here, CH3, then this will have a positive charge. This is a protonated methanol. Talking about this, it's a protonated methanol, and then this will be our product. Another concept which is very important in this topic is the energy diagram for both reactions. So you should know that the SN2 has one step reaction, while SN1 has two steps. So for SN2, the energy diagram is like this, and then the SN1 is like this. Let us start with SN2. You should know that here, at this point here, this is where we find our reaction, where we have our substrate reacting with the nucleophile. And then at this point, it is the transition state whereby the nucleophile is creating bond with the substrate or the electrophile, and then at the same time the leaving group breaks, and then at this point it is when we have our product and the leaving group. If you've studied SN2 reaction, you'd understand this. This is the transition state. This is where the reaction takes place, whereby the nucleophile start to attack, at the same time the leaving group leaves, and then this is where we have our product. While we are at SN1 reaction, this is where we have this point, this is where we have our reaction with nucleophile, and then the first maximum point, or the maximum point, it's where we have the first transition. We have two transitions in SN1 reaction. This is where we have our rate limiting, or the formation of carbocation ion. This is the first transition state, and then we have our intermediate. This point we call it the intermediate, and by the way, SN2 doesn't have intermediate, and then this will be the second transitional state or transition state. Then this is where we have our R bonded with nucleophile and our leaving group here. So the difference is that SN1 has two transition states, including the rate limiting step, and it has the intermediate state, whilst SN2 doesn't have intermediate state. On the first lesson video of SN1 nucleophilic substitution, I did mention that the most stable substrate for SN1, by the way this is SN1 mechanism, is the tertiary, followed by the secondary, the primary, and the methyl. You should know that the tertiary works best with SN1 mechanism, whilst the tertiary doesn't work pretty well with the SN2 mechanism because of the steric hindrance of the tertiary alkyl halides. But you should know that under SN1, tertiary alkyl halides, they are very much stable and they work best with SN1 mechanism. And also SN1, it is not favorable to the vinyl and the aryl halides. So those two, vinyl halide and aryl halide, do not go SN1 and SN2 mechanism or reaction. And you should know that SN1 normally uses the nucleophiles which are relatively weak, because strong nucleophile will force the reaction to undergo the SN2 mechanism, which is the second order reaction. So normally SN1 uses, or a stable SN1 mechanism usually prefers weak nucleophiles. And you should also know that SN1 reaction, if the nucleophile is uncharged or it is water or alcohol, we have step number 3. I think I did cover that one. And SN1, it's a 2 to 3 step reaction. Now the next concept I want us to cover is the stereochemistry of SN1. Now to recall, we know that SN2 reaction, it has a stereospecific when it comes to the attack of the nucleophile. Now if we look at one of the examples that we've looked at, we know very well that in this case our nucleophile will attack from the back. That is the stereospecific. It has to attack from the back because we know that our partial negative leaving group will actually have a force of repulsion with the nucleophile, which is also negative. So if this is partially negative and the negative charge from the nucleophile, we are going to have a force of repulsion. So that is why it will attack from the back. That is the stereospecific of SN2 reaction, to attack from the back. But you should know that when it comes to SN1 reaction, it does not have any stereospecific, so it can attack from the front or the back. And again, we know that attacking from the back, we are going to have an invasion configuration. Looking at the lesson series of SN2 reaction, it fully explains this invasion configuration. Now looking at SN1 mechanism, it has two types of configurations. So let us look at the stereochemistry of SN1 reaction. Remember, it can attack from the front, back, top and bottom, meaning that it can attack in all different directions compared to SN2 reaction. If our leaving group is at the top, it will attack from the back. If it is at the back, it will attack from the front. If the leaving group is at the front, it will attack from the back. If the leaving group is at the bottom, it will attack from the top. So looking at SN1 reaction, let us look at one example to explain the stereochemistry of SN1. Suppose we have the substrate where we have let's say CH3, 2. Then we have CH3 here. We have Br here. And then we have CH2, CH3. So this is our substrate. And then we know very well the first step will occur, whereby it is the rate limiting, I mean. The leaving group will leave, and then we have CH3, 2 here, CH3 here, then we have CH2, CH3 here. Actually, the proper way to draw this, since we no longer this leaving group, which is more electronegative compared to all the groups here, the proper way would be like this, so that it is possible for the nucleophile to attack from the top and bottom. So in this case, we have a carbocation, and then it will react with our nucleophile, which is step number 2. So we can go ahead and draw our step number 2. Just redraw CH3 CH3 2. So in this case, by the way, this is a carbocation ion. In this case, our nucleophile, which is ethanol, let us use ethanol, which is CH2 CH3, and then we can put our oxygen here. It's OH here. This is ethanol. What will happen is that our nucleophile can attack from the top or it can attack from the bottom. When it attacks from the bottom, now I want us to relate this to the SN2 stereochemistry. We know very well that our substrate had our living group at the top. So according to the SN2 reaction, we know that the nucleophile will likely or will prefer to attack from the bottom so that it can yield a inversion configuration. So in this case, the one that attacks from the bottom, it will yield an inversion configuration, and then at the top it will be a new configuration which we did not discuss in the previous lesson series, which is the retention of configuration. So you should know that if it attacks in the same direction whereby the living group was, it will have a retention of configuration, and then when it attacks from the back, which is normally used by the SN2, it is still an inversion configuration. So if it attacks from the top, we are going to have a product like this. Remember, this is a retention of configuration. CH2, it's actually CH3, 2 here. And then we have our O, CH2, CH3. By the way, this is the final product after the deprotonation. So I simply skipped the step whereby we deprotonate. So we call this a retention of configuration. And then if it attacks from the bottom, we are going to have a stereochemistry like this. CH3, 2 here. So you can see this one, it's an inversion configuration, which is the one that you're used to.